Everybody. Before we start, I just want to mention this is a workshop, so there's actually code and data available online. You can find it via the Sloan website. There's a Dropbox. You're welcome to follow along with the code, or you can just pull it down afterwards. Use it however you see fit. But I'm going to take you through how we at FanDuel think about pricing up sports markets and how you might go about doing the same thing. So my name's Keith Goldner. I'm the Vice President of Data Science at FanDuel. There's the link if you have your laptop and want to pull it out. I lead the sports modeling and innovation team, which is a fancy way of saying we model sports as opposed to there's other data science teams that focus on customer behavior and marketing and risk and that sort of stuff. Our job is essentially to put out the probabilities and lines that you can find on our website that you can bet on, and to try to do it as accurately as possible. So generally, here's how it works. Most of you are just familiar with seeing the lines on your phone. Somebody has an idea for a new market. The traders are kind of the lifeblood of what we do at FanDuel. They are the ones who are either putting stuff up on site or monitoring the different markets, watching it while stuff's going live, seeing if anything needs to be adjusted. And they're essentially my team's customers. So we are trying to make their lives easier by predicting the most accurate things that we can and predicting as many things that people might actually want to bet on as possible. So there's kind of 3 tiers of projects that we work on with them. The lowest are ad hoc requests. So they might come to us and say, okay, what is the probability that the opening kickoff in the Super Bowl is a touchback? And we will run a query, build a quick model, send it over to them. They can kind of use it as they see fit. The middle tier is dashboards and tools, usually that we build ourselves to help them self-service and, again, generate these probabilities. And the largest are these large-scale machine learning, data science, simulation-type models, depending on what the task is at hand. And that's to price up stuff live and all the different derivative markets that we use. So today I'm going to take through a specific example. This is supposed to be interactive. It's a workshop, so I'm going to ask you questions. If you have any questions, feel free to ask me at any given time. I'm happy to stop. It's supposed to be informative and want to make sure people are getting something out of it. So the market that we're going to try to price up is which team will score the most points in the divisional round. So in the NFL, in the divisional round, there are 4 games. That means there's 8 teams, and any one of them could score the most points in any given week. And actually, you could have multiple teams score the most points in a given week, which I'll dive into a little bit later because that complicates things. And I'm going to talk about how we might think about pricing that model up. So first, one of the first things you need to do when building a model of any type is think about what your target is. What are you actually trying to model? So in particular, what might a column or columns in your data set look like that you're going to predict against? So I'm going to open this up to everybody. What do we think the target variable is, or what that column is going to look like? What are we actually trying to model? Anybody have any ideas? The sum of the 2 scores. Anybody else? Yeah. Above or below the spread. Okay. Anybody else? Again, the market that we're trying to price is which team is going to score the most points this week. Yeah. Each team's total points. So trying to predict how many points each team gets. Any other ideas? Cool. All right. What we're actually trying to predict here is a binary indicator. We're trying to say yes or no, did a team score the most points that week? So what we ultimately want is for each team, what's the probability that that team scored the most points? And that means in our data set, the final column's either going to be, depending on how you set it up, an ID for the team that actually scored the most points, or a 1 or a 0 saying, yes, this team scored the most points, no, this team didn't score the most points. You can also, there are other options around continuous models. If you were trying to predict the actual number of points that a team scores, that's more of a continuous problem that you're dealing with. But here it's a binary problem. So essentially, for every week in our data set, we want to have the 8 teams and the 1 team that scored the most points. So 0s for all the other teams, and then a 1 for the team that scored the most points, unless there's a tie. Again, we'll get into that a little bit later. Just one call out here for anybody who has gotten into data science. There's a famous data set called the MNIST data set where it's a lot of handwritten numbers, and you're trying to use models to predict which number it is. This is actually a very similar problem to that. Here's an example of it. You feed it into the machine learning algorithm, and it gives you the probability of it being any of those numbers. Obviously, it's most likely a 9 in this case. But ours is the same thing. We're trying to feed in information about the teams and generate the probability that any one of those teams is going to be the highest scoring team that week. Okay, so given our target variable, the next step is to think about what types of models we might use. You'll notice that a huge portion of this presentation is brainstorming. My general approach is that you want to have the entire thing thought out and all the different options ahead of time, as opposed to just immediately diving into a data set and then trying to figure out where it takes you. So given that what we're trying to predict and what our target variable is, anybody have any ideas what types of models we might try to build? Anybody? Linear regression model, okay? Logistic regression. Decision trees, all good answers. Anyone else? Neural net with softmax. Okay, all good answers. I just wrote down a few here. You can do kind of classical machine learning algorithms that are classification algorithms. So a linear regression in this case would not work because that's more predicting a continuous variable, but logistic regression, decision trees, neural networks, they could all be used here to try to predict it. I'm pretty shocked nobody said this given the title of the talk, but we're actually going to talk a lot about simulation models here, and that's what we're going to use. And so diving into a simulation model, my first question is, does anybody know like why we might want to use a simulation model, or also why we might not want to? What are the kind of the pros and cons of using simulation?
Simulations might produce random effects that models may not be able to accurately explain.
Cool, yep, potentially random effects being explained. Anybody else? Yep.
You don't have a lot of data, the simulation can help like make up more trials and more data to work with.
Cool, so he said you can make new data essentially using the simulation if you don't have enough of it. Anyone else? Yeah.
There are other things that you're trying to model that are correlated with it, and you don't need a whole separate model to build.
Cool, yep, so when you have correlated things in particular, simulations can be really good. So that's the main reason that we're going to use it here. I'm going to use that to dive into the pros and cons. So the main pros of using simulation model, like you said, is when you have really complex joint distributions, those are much easier to tease out in a simulation model than in a machine learning model. And what I mean by that is in our example, there's a lot of interaction. So the first interaction is that you have two teams playing against each other, and that means one team's score is going to be related to the other team's score. If one team scores a lot of points, the other team is going to be trying to score a lot of points. If one team has a really bad defense, the other team is going to be much more likely to score a lot of points. So that's the first interaction that we're dealing with. And the second is that how likely a team is to be the highest scoring team is highly dependent on what other teams are playing that week. So if there's just two games going on and the Eagles are playing in one game and the other two teams are the Texans and the Jets, which is likely to be a much lower scoring game, the Eagles have a much higher chance of being the highest scoring team in that game, in that week. But if you have the Chiefs playing in the other game, who is a better offense, the Eagles are a lot less likely to be the highest scoring team. So we have these interactions that are much more difficult to tease out using classical machine learning algorithms. The second is simulations tend to be easier to tweak when there's rule changes. So one of the things we see a lot is a rule change happens and then we have no data to represent that new rule change. So an example is when the extra point was moved back in the NFL, if you had a win probability or if you had an algorithm to predict what the final score was going to be, that was just a neural network or an XGBoost or a logistic or any sort of complex machine learning algorithm, you would not really be able to take into effect the sixes and eights that you're going to get for scoring when the extra point was moved back, whereas if you have a simulation engine, you could tweak the submodel that says, here's the extra point, here's our estimated probability for what we think the extra point's going to be, and that would immediately flow throughout the entire model. And the last is that it does a really good job of modeling real-world sport variance. So because you're simulating things thousands and thousands of times, potentially hundreds of thousands of times, you're going to get a lot of crazy outcomes, but stuff that could actually happen in sports. So just take the example of like flipping a coin over and over again. If you simulate out 20 flips 10,000 times, like you're likely in there to get 10 or 15 flips in a row at least one time, and then you can kind of see the total variance that you would get from the simulation approach. Now, simulations aren't all good, otherwise we would use them for absolutely everything. Here's some of the reasons that you might not want to use them. In all machine learning, there's the old adage of garbage in, garbage out. If you have bad inputs, you're going to get bad outputs, bad predictions. In simulations, this is especially true because simulations tend to be more complex, and you get to the next one, which is that if there's a bit of a butterfly effect, if there's something wrong in your simulation engine, then that can get compounded over and over again, not only throughout the simulations, but throughout kind of the different components within the simulation. So the second part is that it can be complex to debug if something's going wrong and it's not your inputs. You have to figure out where in the simulation engine, this complex technical thing, that things are actually going wrong, and that can be a lot more challenging than just a simple logistic regression where you can look at the inputs and the coefficients. And the last is that generally building a simulation engine requires a lot more subject matter expertise and a lot more technical expertise. There's a lot of people who, with traditional machine learning, will take all the variables that they can, as many columns as they can, throw everything at the wall, see what sticks. It's not the best approach, but you can still get decent predictions out of it. To build a simulation engine, you need to know the rules of the sport or whatever it is that you're trying to model, and it can be a lot more complex in that sense. So those are the main pros and cons of simulation. Okay, what will delivery look like? Again, this is all brainstorming. We haven't said for sure we're going to use simulation, but and what the target's going to be, all that sort of stuff. But I like to think about what delivery is going to look like very early on in the process. Far too often I've seen someone build a model and spend months and months and months eking out little data points in accuracy, little decimal points in accuracy, and then it gets kind of like put up on a shelf and never gets used. And if your model never gets used, no matter how accurate it is, it has no value whatsoever. So from the very beginning, I like to think about delivery. I like to build a very simple model and productionize it almost into a beta, and then for us, we like to get it in front of the traders to get feedback while all the while we're refining the model and trying to make it as accurate as possible. For what we do, there's kind of two main avenues of delivery. The first is the optimal solution. It's where we have a live feed coming in. It feeds into a database or some queue system, runs the model that we've built on it, goes to the server. The traders are just kind of monitoring it, and then it goes up live on site. The second is kind of the more manual version where we've built the model. The traders have a dashboard or a tool. They can put it in, and then sometimes either with one click or manually, they can put that stuff up on site. We're going to talk about the second one here just for simplicity. The top one requires a lot more engineering and building out the entire pipeline and dealing with latency. So for the simplicity of this presentation, we're going to talk about the second one. Okay, designing the simulation. We've got these 4 games going on, these 8 teams. What does this simulation engine actually look like? Before writing any code, we're going to map it out so that we can then go on build it. You've got your input, whatever the features are that we decide. They're going to run into the simulation engine. That's going to run thousands of times, 10,000 times, 100,000 times, and then we're going to get the output, which is for each simulation or overall, what's the probability of each team being the highest score. Inside the simulation engine, the very first thing we need a submodel. This submodel is going to be a probability distribution of how many points each team is capable of scoring. So what's the probability that the Chiefs score 24 points, 25 points, 26 points, et cetera. Once we have this submodel, we can then roll the dice, and it's going to spit out a random outcome based on that probability distribution. So in this first simulation, Kansas City beat the Jaguars 42-13. We do that for all of the games, and then we say, okay, the Chiefs were the highest scorer this week. Let's mark it down. We run the simulation 10,000 times. How many times were the Chiefs the highest scorer? Out of 10,000, that's your probability that we can then put forward for anybody to bet on. All right, now we have to do the same process, which is designing the submodel. So in the submodel itself, what are we trying to model? What would that target variable look like in our data set? Anybody have any ideas? So, yeah, go ahead. The number of points scored by that team. Anybody else? Yeah.
Probably distribution over the scores.
Correct, the probability distribution over the score. So we're going to, I kind of just said this, but we're going to try to figure out exactly what the probability of each scoring outcome is. So for any given thing, what's the probability of them scoring 0 points, 50 points, 27, because then we can roll the dice and map it to that. To do that, what types of models might we use to get a probability distribution? Anybody? Any ideas? Yep. Monte Carlo, okay. Nobody? Histogram, just find the frequency, so an empirical model looking historically at how it happened. Did you have? Yeah. An ordinal regression model where you're trying to predict the basically each next number in it, so like an ordered logistic regression. So these are all good answers. We said the empirical model. You can use an existing distribution as well, so you could take something like a normal distribution and fit it, and then you could use a classification algorithm as well, especially one that's ordinal is a good fit for it. In our case, we're going to use a normal distribution. I'm going to add the caveat that scoring points in football is not exactly normally distributed because of key numbers, but I'll talk about that a little bit more when I'm going through the code. Okay, then we have to figure out what features you would do. So for any model that you're building, you need to know what features, what things are actually going to be predictive. And in our case, let's talk about, we're trying to do points scored. What's going to have the biggest impact on how many points a team scores? So if you were trying to predict the distribution of how many points a team scores, what features might you want to include in your model? Offense, I heard. Home and away. What else has an impact on how many points a team scores? Weather. Opponent, yep. Player skill. Okay, cool. These are all great answers, I made a list, non-exhaustive list. Your offensive efficiency, your opponent's defensive efficiency, weather, we said team pace, teams that play quicker are going to score more points. Teams that play slower, you're going to score less points. Your opponent's pace, there's an interaction there. Defensive efficiency, depending on how good your defense is, that actually is going to impact how many points you score and are scored in the game, and same with your opponent's offensive efficiency. Somebody said player skill, injuries, that sort of thing, all potential features that we could be using. The next thing, though, is how do we quantify this feature? So weather, for example, we just said how weather has an impact on it. It's a feature we want to use, but what's the actual stat in our data set? What's the column or columns going to look like? And in particular, how might those stats be biased? So we want to give the most accurate representation of whatever the feature is, whether it be weather or offensive efficiency, and figure out what actual data points to use. We see this a lot in data science. People know what impacts it, but they don't know how to measure in an unbiased way what impacts the target variable. So if we wanted to quantify offensive efficiency, what actual statistics, like what column or columns, do you think that we should use to measure offensive efficiency in the NFL? Yards per play. What was completed passes? Expected points added. What was that? DVOA. Okay, cool. All good answers. Again, I made a short list here. Points scored per game, yards per attempt, expected points added, the league rank. You hear a lot on broadcasts like, oh, they're the 5th ranked offense. You could use any of these, but you want to think about the biases. So in particular, when you think about points scored per game or league rank, that's not taking into consideration who their opponents were. If you were top in your division and you're playing a lot of really difficult opponents based on your schedule, as a result, you want to make some sort of adjustment for that. And the second thing is situational. So when you look at something like yards per attempt, 2 yards on 3rd and 10 is a lot different than 2 yards on 3rd and 1. And so that can be a biased, misleading stat. That's why stuff like expected points added and DVOA can be better for quantifying offensive efficiency. Okay, what we're actually going to use here is a little simpler. We're going to use a metric called implied team total that takes into consideration all of these things. You can see on the right here was the implied team totals for that given week. And what implied team total is, it's basically, as the sportsbook, what are we predicting the total to be for each team? The way that's derived is from the spread and total for the game. It's a simple equation. You take the total divided by 2 and the spread divided by 2, and you get the implied team total. So you can see in this case, this was Dallas versus Washington. The spread was 4, the total was 48. So we're predicting the score is going to be 26-22. They add up to 48, and the spread is 4 points. Next, we're going to talk about the data. Yeah. Sure. Yeah, you absolutely could. Yeah, exactly. Yeah, if we were predicting the spread and total via a different model, yeah, that could feed that into this to get the implied team total as our feature. Yep. So I'm going to talk about data next. If you came to the workshop last year, this is going to be a lot of repeat, but data is obviously the most important thing because of garbage in, garbage out. How do we collect, organize, verify, clean, and engineer our data? Collecting it, you're usually going to do it via an API or a database or scraping website. We have APIs that we use to load up our database in our case, but it just depends on your use case. You want to think about what format do you need your data in. Generally, when you're building machine learning algorithms, you want your columns as predictor variables. and then one column for your target, or potentially multiple columns depending on the type of model that you're building. So as you're extracting that data, you want to be thinking about how am I actually going to put it in a format such that I can load it into Python or R or whatever it is that you're using to build a model. Then you need to clean your data and verify it. Here's the things that you want to think about. I'm going to go through them one by one. So first is duplicates. If you look, you've got these two rows with the eagles where they look identical, but actually when you add context, they're very different games, and so rather than just deleting the duplicate, you want to make sure that you have context and that you have individual observations. Similarly, these are names in our NFL database, and you can see there's 5 Brandon Williams. You want to make sure that you have unique identifiers so that you're not attributing features to the wrong players or teams or whatever it is. Next is clerical errors, so going through your data set, looking for impossible values, wrong data types. 10.5 implied total, it's not impossible, but it's very unlikely to have something that low. We'd want to go back and look, see if we had bad data or if we can replace it. We have a variable here for whether it was playoffs or not, and there was a string yes instead of a 1 or a 0. We'd want to fix that, figure out why that was like that in our data set. And then we have a target of -21. You obviously can't have negative values. Maybe it was just somebody input a number wrong. We want to, again, not necessarily just throw it out, but figure out what's going on because there could be other issues in our data set as a result. Handling missing data, this is very similar. It's just a specific type of kind of clerical type errors. That's like null values and NAs and empty things. In the first one, we have no implied total. That's supposed to be our feature that we're predicting based off of. We obviously can't do that without that feature, so we want to see why that was wrong. If we can't figure it out, let's delete it. Then you have null values for playoffs here. Initially, you might think that's bad and we'd have to figure it out, but maybe in our data set, anytime it wasn't the playoffs, it's listed as null as opposed to being a 0, so we'd want to go in and fix that, turn them all to zeros. And then the last is we have no target here. Maybe somebody did an Excel, did a bad VLOOKUP, and you ended up with an NA, and you'd want to go and figure out how to fix that. Check outliers. A lot of this brainstorming process is, and modeling in general is like common sense. Histograms are your friend for everything that you're doing when you're building models. So here we see a value below 0. We'd want to know why. That's obviously not possible, why that might have happened. We see a score over 80, which has never happened before in the NFL, so we want to know why, and then we probably still want to check those low values and those high values to make sure that they're kosher. And last, another sanity check, graphing it, making sure it makes sense. So this is a graph looking at implied team total versus the actual score. We would expect in general the trend line to go up as if we do a good job as a sportsbook, that means that we're predicting it well. The first one looks pretty good. There's some lower values, although I think the x-axis might be truncated, making it a little confusing. But on the second one, we see that, like, you probably might not even be able to see that on there, but the trend line goes down after about 25, and that would make us think that something is wrong. We'd want to go back, see what's wrong with us pulling the data. Last is feature engineering. So feature engineering is basically when you combine the raw data points that you have to have a more predictive feature. In our case, I talked about this already, implied team total is technically an engineered feature that we took the spread and the total as the inputs to create it. That's just one example of feature engineering. Last year, I talked about using weather data. You had wind direction and wind speed, and you could actually combine them into a vector to look at we were looking at the probability of a field goal and what's the wind going straight at the field goal and what's the wind going across, as opposed to just the direction and the wind speed. Next step, let's build a model. So again, I like to start simple. I like to have delivery. This is just an Excel model, an Excel simulation model, where we used implied team total as the mean and the league average score, the variance in that, and treated it as a normal distribution and simulated it out. And you can see the price is what came from this Excel model, and the actual prices that we had on site on the right, they're not dramatically different. Wouldn't be a terrible place to start. Get it in front of traders, build out that pipeline so that you can continue to iterate and there's actually something functional going on. And to show just how simple this is, the actual formula used for simulating it is right up here. It's taking we're rounding because you need a whole number for the actual score. The normal distribution inverse of a random number, that's our dice roll of the implied team total and the variance for the league. That's all in Excel. I want to briefly talk about garbage in, garbage out. So we talked about using average points per game potentially as our feature in this. So this is if we ran that same simulation with average points per game. The problem with average points per game is it's not looking at who your opponent is for that week. So the Chiefs, who are playing the Jaguars, their probability is much lower than it actually was because the Jaguars are not a very good defense. And then Dallas, who was playing San Francisco, who has a very good defense, their probability was significantly higher in this. You can show that by putting in a bad input, even one that seems like it might be a good input for the simulation that we're doing, you can end up with really bad outputs as a result. Deciding on the number of simulations. So this is a bit of an art form. The biggest component is how much time do you have to make these predictions. So if you're making a prediction once a week, you can run simulations overnight and as many as you possibly need. If you're doing stuff in real time, you need to be able to do it in seconds or milliseconds, and that's going to be the single biggest consideration. The other part of it is accuracy. The more simulations you run, the lower the variance is going to be in outcomes, and you want that to be as low as possible. You're going to have an epsilon that you don't want to go bigger than, which means that if I was only simulating things 100 times, and in this case, the Chiefs came out the first time I simulated 100 times at 20%, and the second time at 25%, those are really big differences in terms of the probability of outcomes occurring. So you want to make sure you're simulating it enough times such that that epsilon is not that big. The last part of this is just that if you can't get it quick enough, then you have to look at optimizing your code or potentially coming up with some other solution. All right, testing the model. So I'm going to go through the code fairly briefly here. Again, this is all available online. If you have any questions about what I'm doing, stop me. I'm honestly not a huge fan of Python notebooks, but they're because they don't necessarily teach the best coding practices, but they're very good for presentations and kind of procedurally going through stuff. So to start, we import all of our packages in Python. We're going to read in our data set, take a quick look at it, make sure that it looks okay. Next, what we're going to do is we're actually going to duplicate the data frame down. So in this case, it was 1 row per game. And what we actually need is 1 row per team because we need to know, okay, are the Chiefs going to be the highest scoring team and are the Jaguars going to be the highest scoring team? So we duplicate it down, 1 for the home team, 1 for the away team, and then we're going to do our feature engineering. So adding in our implied team total, our opponent's implied team total. Now we've got a big data frame that's set up the way we want. We want to look historically, okay, which team actually was the highest scoring team of the week. So we're going to add that in, merge it into the data frame. And then I mentioned this before, but you can actually tie to be the highest scoring game in a week. So if the Eagles and Chiefs both scored 40 points, that's an outcome that we have to account for. At the Sportsbook, you get dead heat rules, which is where you essentially, in that case, would get half of the payout that you want. So we're looking back at our data. There's a decent number of weeks in our data set where teams did tie to be the highest scoring team of the week, and we're going to need to account for that. Again, talked about sanity checking, histograms being your friend. This is a look at team score distribution and how often, based on that score, they were the highest scoring team. So the orange is when they were actually the highest scoring team compared to their score. Similarly, we're going to look at the implied team total, and you can see that the higher up your implied team total is, the more often you were the highest scoring team of the week. And then we're going to look at implied team total versus actual score and when those were the highest scoring team of the week. Again, just getting a good idea, making sure our data makes sense, that we're happy with it going forward. All right, I'm going to talk about the normal distribution a little bit. So generally, like I showed with the histograms, scoring is normally distributed. In reality, it is not. In football, most of the scores are in 3s and 7s. That means that a score of 21 or 24 is much more likely than a score of 22 or 25. So as a result, a normal distribution is not a perfect fit. But for the sake of this presentation and for simulating it out, we're going to use a normal distribution centered around our implied team totals. Okay, now we're going to generate our simulation function. We got our, this is to get our standard deviation for the league-wide thing, which was like 10 points or so, 10.3 points. Here's our simulation function. This is the entire simulation happening. So we're going to put in the number of simulations. We're going to simulate it out. In this case, I think 10,000 times is the default. We're going to get the random, this is just like the Excel function, the random normal variable with our implied team total as the mean and the league scoring standard deviation. We're going to round it to a whole number since points have to be a whole number in an actual game. We're going to figure out who was the highest scoring team that week. We're actually going to do this for all weeks historically throughout. I forget what the data set we used was, but we went back like 10 years. We held out 2021 and 2022 as a test set. We're going to simulate them all out. We're going to account for dead heats by looking for ties here. And then if we just pass in 1 week, just for simplicity, we're going to print out what those probabilities are so that later when we are looking at the divisional round, which is what we're trying to predict, that we can get the actual output for it. All right, so here we're actually running the simulations, run it 100,000 times. We're going to print out some accuracy metrics, so AUC, log loss, Brier score, to see how accuracy it is. Because next what we're going to do is we're going to use a traditional machine learning approach and compare it and see which is more accurate. So here we're building a logistic regression model. This is fairly simple. For each team, we're treating them independently, which we already talked about. There is a correlation between them. There is a joint distribution. So just off the bat, we know it's not going to be a great solution. And similarly, with these types of models, it's going to be much more difficult to predict ties, because you're just going to get the probability for each individual team. So we have our testing and our training set. We build a logistic regression. And then what you end up going to get is, because they're all independent, you could have probabilities that add up to over 100% or under 100%. So we're going to want to scale them to 100% so that we have full probabilities. And that's what this softmax is here. We're going to get the same accuracy scores. They're pretty close. The simulation was better on all of them. So we're going to be pretty happy with that. And then we're going to look at the divisional round and print out our probabilities. And so those are the prices that we could then put on site for people to bet on or send to the traders to use how they see fit. All right. Any questions, I guess, up to this point before I kind of talk through the stuff after the code? Yeah. So we the random number is a decimal. It's between 0 and 1, and then based on that, you're taking a number out of the distribution. We did a normal distribution, so it is continuous, and then we're rounding it to the whole numbers. Oh, for like the implied team totals? Yeah, you can still use that as a mean for the normal distribution because, again, the normal distribution is continuous. Yeah. Yeah.
Why don't you like Jupyter Notebooks?
It's very procedural code. It's not reproducible code. And so when you're building full models and you want to have shared code, you want to have well-documented code, you want to have well-written code, and usually reusable code is the big part of it. Jupyter Notebooks tend to be not very reusable, and most of the Jupyter Notebooks that I have seen tend to be fairly hacky in that the variables aren't written very well, and somebody can't necessarily just come in and see what's going on. They're good for presentations if you do the full markdown, and then you can really show the logic that you're going through, but in terms of like extensible, reusable code, they tend to be suboptimal. Cool. Yeah, go ahead.
What's the difference between like using empirical data that would kind of show the 3s and 7s versus like a normal distribution that like kind of doesn't?
Yep, yeah, empirical data generally would be fine. You just can sometimes run into sample size issues. And so in this case, would you be using just the Chiefs' empirical data to predict the Chiefs, or would you be using the whole league empirical data? And if you only have 12 weeks of data, or if they had coaching changes, then it might not apply in that case. Yeah.
How much better can you get using a better distribution than normal?
You can get a lot better, especially when you take into consideration the interaction effects, which we're barely taking into consideration here because all we're really looking at is the implied team total, the offense versus the defense. If we were, for example, simulating out each individual game and seeing the impact of one team's score on the other team's score and doing that for all of them, you could get significantly more accurate. All right, I'm gonna talk through the rest of this, and then there should be tons of time for questions afterwards. So model trade-offs. These are just all things to be thinking about when you're selecting your model type. Are accuracy, explainability, who are your stakeholders? If you have a black box neural network and you really need to be able to explain to somebody what you're doing, it's going to be much more challenging than in a simulation. You can look at the individual components and explain that to somebody. Integration, a simulation is going to be much more difficult to integrate than a logistic regression, which is just one line of code. Runtime, I already talked about. If you have to run a simulation 10,000 times, 100,000 times, that's going to take way longer than doing a logistic regression. And then maintainability, how easy is it to update depending on new rule changes, new data, all that sort of stuff. You want to be thinking about that the whole time, not necessarily just after you have built the model. Next, you got to test the model. So your goal is to act like a first grader and try to break it. Ideally, you want this to be automated, but a lot of times it's a manual process. You want to try normal inputs. You want to try bad input values, bad input types. So here I put in a negative number to our Excel, and it still generated a probability because a normal distribution, you can actually go below 0. That's another reason that it's not a perfect distribution for doing score, because you can't have a score below 0. We'd want to have a warning for the traders that, like, hey, you put in a negative number here. Make sure that you're doing the right thing. And the last thing is edge cases is a big consideration. So looking at what the top implied team total was and the bottom implied team total and making sure that they still make sense. And next is productionized model. So again, I built a really simple tool. It's essentially an Excel worksheet here that you can watch as the simulations each time I run it. You're going to get new in the simulated points column C. You're going to get new ones. So Buffalo was the highest scoring team here. Here it was Jacksonville. They scored 56 points. And then you can run it hundreds and however many times you want to run it, and it's going to generate the probabilities for you and eventually the prices for the traders to do. So our job in this case, if it was like an ad hoc request or a tool that we wanted to price this up every week, we could literally deliver this to the traders. It's obviously not super robust. It's not what we would actually deliver, but we could do this, and then we have prices on site for this market. I think that's just about everything. Oh yeah, the last thing is iterating on it. So once you build a model, your job isn't done. You want to test it, especially as new data comes out. You see in baseball with the different types of baseballs that the scoring changes dramatically. You want to make sure that your model still applies to whatever the data is, and then continue to test, continue to update, continue to iterate on it. Cool. Yeah, that's everything. What questions do you have? I know there were some other questions before. So did you? Yeah, it varies based on what the task at hand is, and it depends who the data scientist is and what the requirements are. I generally want my data scientists working where they're most comfortable, so we have some in Python, some in R, but for a lot of the really low latency stuff, those languages are not fast enough, and we work with more scalable, more robust languages to build those models, or at least to deploy those models, I should say. Sure, yeah, I'm probably not the best person to talk about that because that's more in the engineering domain, but we obviously need to get really fast data because people are betting on it live. That needs to come in. It ideally needs to be accurate, and if it's not accurate, it needs to be corrected in real time, and those are the inputs that go straight into the model. That's part of the reason why we still want traders watching everything that we're doing, because if a data provider sends us a bad input and that goes into the model, which is going to come with bad probabilities, a trader would immediately catch that and flag it, correct it, or suspend the market if we had bad data, at least until it was corrected. But yeah, the actual tech components, I would say, probably better to talk to our engineering team. Yep. Yeah, it depends on the model and the sport, because something like baseball, there's a lot more time in between pitches, and even in the NFL, there's a lot of time between plays, whereas NBA and NHL, they're happening nonstop, so it varies based on the sport. But yeah, we have requirements essentially for each sport. How quickly can we get the data and probabilities through from feed all the way through to pushing it on site, and we have to, whenever we're developing new tools and adding new stuff to it, that means that the payloads get bigger, and we have to make sure that we're continually optimizing to bring it down as much as possible. For teasing it out? Yeah, so generally I think simulation is the best way to account for correlation, as if you can do it effectively, but there are other ways to model joint distributions using correlation matrices and that sort of stuff. Again, it's kind of specific to whatever the project is that you're working on, but there are other methods to doing it depending on what you're trying to do. Yeah.
You had the scale that had compute time and then accuracy on one side. I think there's another aspect that you can put to that, which is you can invest money by spending a compute resources to drive down that compute time, but how important is that compute to you at that moment?
Yep.
What do you guys think about that?
Yeah, 100%. Yeah, the easiest lever to always push when you're worrying about speed is, can you parallelize this and throw a bunch of CPUs at it, essentially. So that's usually the first thing that engineers go to is like, hey, if we're having troubles with latency, let's spin up more resources. But ideally, you want to optimize code, come up with solutions to make it work. But that is always a lever that you can push, for sure. Yep.
How do you handle confidence in simulations? Because maybe one submodel has better predictability than another one, maybe passing yards versus sacks.
Yep.
How do you handle that and communicate that to the crew?
Yep. So in general, like we build robust testing frameworks so that we're looking at not only the full simulation output, but the submodels, and how do those look compared to real data? So we're trying to test each individual submodel as we're building it. In this line of work, you have to be super humble. You have to know that there are really sharp bettors out there who are gonna beat you, and so you can't come out and say, I'm 100% confident in my price, we're not gonna move it. You wanna use all the good information that you can to come to the true price, the most accurate that you can, and a big part of that is we are confident in what we're doing, but we know that there's other good information out there, and our traders are subject matter experts, and our data scientists are subject matter experts, and all of that information together we're using to make decisions.
How much do you account for opponent's pricing, like arbitrage betting and your pricing?
Yep, yeah, it's honestly, it's a similar answer to that. It depends on how confident we are in the price. There are situations where, based on bets that we've taken and our models, where we say, hey, we feel pretty good about this price, we're willing to be exposed to those like arbitrage opportunities. And there's other times where we might not have as much confidence, where we're gonna, I mean, the market information, again, is good information, and anybody who tells you not to use that in your predictions probably would not do very well in the sports betting space. Yeah.
Competitor sportsbook odds ever get factored into the model itself for the way the markets are priced?
I don't think we would look at like one specific competitor, but generally we use other competitors to essentially estimate where the market is at. And like I said, depending on what the market is and how confident we are, we're going to use any good information to make predictions.
You showed in your delivery process that downstream traders are using the model. Is there any circumstance, do traders have universal control over what the odds are? If they get the model and they see something they don't like, can they go in and manually?
It depends on the situation, but generally the traders are the last line of defense, and they're one of the competitive advantages that we have is that we have such talented traders, and so if they see something wrong, then they're going to either adjust it or suspend and go from there. One of the reasons that we feel like we can build such good models because we sit so closely with the traders and have this back and forth and trying to progressively improve everything that we're doing.
How do they, I assume this is done by the traders, how do they apply VIG to the odds that you're applying?
Yeah, again, I'm not the best person to ask. That somebody on the training team is, and we have traders here. You can come out to our booth. But generally, it depends on what the market is and what the odds are that are going on, and we have kind of standardized things, again, based on how confident we are. The core markets where there's a lot of liquidity and we're pretty confident in it, the VIG on those is going to be significantly lower than maybe some obscure pickleball player props, where the VIG would be much higher because there's uncertainty there. Cool. Any other questions? Cool. Awesome. Thank you very much for coming. Appreciate it. Again, the code is up on site if you ever want to play around with it, and I'll be here to answer any questions if you have it.